we have a beam with intermediate hinge. This intermediate hinge at D makes zero moment at D. This is the true meaning of hinge, intermediate hinge. We separate the beam into two parts at D. So we have a part AD and another part DC. The part DC is considered to carry the part AD at D. We can observe the method of construction of the hinge D. Since AD is supported on DC, we consider a hinge at D in the upper part AD. We compute its reactions, and those reactions are inverted as loads on the lower part DC at D. The structure is therefore modeled as such. Part AD is drawn above the part DC as it is carried by the part DC at D. And this explains why we have a hinge support at D given once on the upper part. Each part of the two parts must be stable and determinate. And as we mentioned, the support is applied once on the upper part to indicate that it is supported on the lower part. We can determine our reactions. We start solving from up to down. So we have part AD, reactions YA at the roller A, and two reactions on the D support. Sigma moments about D gives YA to be -2, indicating that it was assumed in the wrong direction in our equation. Sigma forces in the y direction equals 0 gives YD equals 2 tons, and sigma forces in the x direction equals 0 gives XD equals 5 tons. And here we are done with AD. We invert the YD here to be a load in the opposite direction of YD on the lower part, and we invert XD to be a load of 5 tons on the lower part, at D of course. Now we start computing the reactions for part DC. We have one reaction at B, 2 at C, and we take moments about C equals 0 for the part DC only, which makes calculations easier and faster. This is the privilege of separating our structure into parts whenever we meet intermediate hinges. So we have 4 by 6 by 3 minus 6YB plus 2 by 9 plus 2 by 12, giving YB equals 19 tons. Sigma forces in the y direction equals 0. We apply all vertical forces to our equations, and we have YC equals 9 tons. Sigma forces in the x direction equals 0. We have only this red 5 tons and the XC, so we have XC equals 5 tons. This gives our reactions for the whole structure AC. We are ready now to compute our straining actions. The computed green reactions here can be applied directly on the whole structure. On the whole structure AC. And straining actions plotted. However, I believe that dealing with each part separately is much easier and faster. So, to plot our normal force, we start from the left-hand side or from part AD, and we consider all tension and compression forces on our parts. So for part AD, we start with node E, this 5 tons. It is clear it is tension force. And we have the 0 from A to E. And E right equals the 5 tons and is plotted on our diagram, constant until we reach D, and we close with this red 5 tons at D on the upper part. Going to the lower part, we have 5 tons tension at D. This means that we will rise on our diagrams 5 tons and constant till we reach C. The green 5 tons at C closes our diagram. There was no need to consider this 5 tons and this 5 tons here at D on the upper and the lower parts of the beam, as those two 5 tons cancel each other on the diagram. And the normal force can be plotted directly from E to C. Shear force diagram. We are searching for all vertical forces, as those are the forces that cause the shear on our beam. We start from AD and then head up to DC. Part AD, we have 2 tons heading downwards at A and plotted on our diagram until we reach D. And those red 2 tons here at D close our diagram. And we go to DC. 2 tons here open our diagram heading downwards for DC until we reach the left of F. To go to the right of F, we add those 2 black tons here and constant until we reach B left. To go to B right, we add those 19 tons here and we go incline 4 by 6 tons for the distributed load. And we close our diagram by the YC equals 9 tons. Again, there was no need to consider the 2 tons at D for the lower and the upper parts as they cancel each other. And the shear could have been drawn directly from A to F left. Now we plot our bending moment diagram. We consider the part AD first. And of course at A and D we have 0 moments as the roller and hinge are located at the ends of the beam. We have 2 moments at E, one at the left side and one at the right side. The left moment at D is computed by 2, this green 2 tons by the arm till we reach E, 3 meters, giving minus 6 meter tons to be plotted upwards on the diagram. The negative sign indicates that the tail of the moment is above the beam and therefore the compression fibers of the beam are downwards. To compute E right, we add the effect of this 12 meter tons. So we have 6 meter tons plotted downwards, positive moment. To explain this more clearly, we have our joint E, our bending moment 12 meter tons. Since this blue 12 meter tons, since we are computing from the left side, we add its effect after settling this moment on the left side in this red sense. So we have our tail here heading downwards, and therefore it is added as plus 12 meter tons, giving ME right 6 meter tons. At D, we have 0 moment, and we compute moment at F from the part DC. So moment at F equals 2 by 3 meters, 6 meter tons, plotted with the tail or the tension of the moment upwards, so minus 6 meter tons here, and we compute the moment at B. From the left part, minus 2 by the arm and minus 2 by the arm of the black 2 tons, giving minus 18 meter tons. We have our 0 moment at C, and we drop our parabola WL squared over 8. So we have 4 by 6 squared over 8, indicating that the distributed load has a second order degree parabola. This gives 18 meter tons a drop. For full course analysis of statically determinate beams, please check the link below.